Hi, and thanks for your interest in my talk entitled Statistical Assessment of Operational Risks for Induced Seismicity from Hydraulic Fracturing in the BC Montney Interpretation. I'd like to start by acknowledging my co-authors at Enlightened Geoscience, Scott McKean and Neil Watson. This talk was intended to follow another geoconvention presentation by Scott that was going to discuss the details of the machine learning workflow we used, but that presentation got inadvertently dropped from the geoconvention program in the transition from a live to a virtual event. That was entirely our fault, not the fault of geoconvention organizers or the session chairs. But as a result, I feel it's important for me to spend a little bit of time on our methodology as well as the interpretation. But as you'll see, this ends up making a lot of sense because the methodology and interpretation are actually quite intertwined. So my outline for the talk includes some background information regarding the motivation for the work, as well as a definition of the study area and a discussion around the sources of the data that we used. From there, I'll discuss the generation of the machine learning models, including data preparation and feature selection, and then I'll address model performance and final feature importance, and what are some of the lessons that we learned in the process of the project. Seismicity induced by hydraulic fracturing was not originally accepted by the global community, in contrast to seismicity induced by other mechanisms like wastewater disposal or depletion of large reservoirs. These mechanisms have been well understood for decades. The figure on the left shows correlation of earthquake frequency with wastewater injection at the Rocky Mountain Arsenal site in the early 1960s. Although hydraulic fracturing has been around since about 1950, it didn't scale up until around the turn of the new century, and it wasn't until about 2010 or 2011 that we started to see well-documented cases of hydraulic fracturing-induced seismicity, primarily in the US and Western Canada. Now there are many known cases around the world. Tolerance for these events is different depending on where you are in the world. For example, in the UK, the magnitude cutoff threshold is usually around 2, and in BC it's more like 4, primarily because of population density. Unlike with large-scale injection, the mechanisms behind hydraulic fracturing-induced seismicity are not very well understood, particularly how the hydraulic fractures induce pressure or stress changes on nearby faults. For example, whether it's a direct hydraulic connection or a poroelastic effect. On the right, we have a cartoon that kind of illustrates this. It's also not really understood how the different operational parameters involved in hydraulic fracturing, like fluid volumes, ejection rates, pumping pressures, etc., relate to induced seismicity risk, if they even do at all. This was the motivation for our study because while we have little to no control on the geological risk factors, we do have the potential to adjust operational parameters if there's evidence that doing so can reduce the risk of induced seismicity. So our study area is the Montney Unconventional Resource Play in British Columbia. The Montney is the most active unconventional play in Canada right now, or at least one of the most active, and it is quite large, stretching from western Alberta into northeastern British Columbia. Hydraulic fracturing in the Montney has been known to induce small seismic events, with some of the largest being around magnitude 4, which occurred in late November 2018. Our project is one of 4 projects funded by Geoscience BC at the end of 2019 to look at induced seismicity in the BC Montney. The study area, as shown here, covers the entire BC Montney, stretching from around Dawson Creek in the south, all the way up to just south of Fort Nelson in the north. It's divided into 2 main development areas, known as the Kaskatinaw Seismic Monitoring and Mitigation Area and the North Peace Ground Motion Monitoring Area. There are several earthquake catalogs available for the study area. We combined 3 different data sets, which are listed here. Approximately 2,300 duplicates were removed, identified as occurring within 10 seconds and 10 kilometers of each other. We calculated the magnitude of completeness for the North Peace and Kaskatinaw regions separately, and also for a combined data set, using 3 different methods: maximum likelihood, which is in red here, goodness of fit, which is in blue, and maximum curvature, which is in green. Events below a unique threshold magnitude of completeness for the North Peace and Kaskatinaw regions were removed because results were quite different for the 2 different regions. Events prior to January 1st, 2000 were also removed. So our final catalog consisted of just under 10,000 events. We used two different completions datasets. One was provided by Geologic Systems through Geoscience BC for use in all of the participating projects. And the other one was the BC Oil and Gas Commission's public dataset. They differed in the total number of wells and in some completions details. In our proposal, we said we'd also look at a limited number of geological factors, and our sources for those included published and public domain maps and datasets, as well as a few proprietary maps. Between the two datasets, operational and geological, our original number of features was 82, and as we'll talk about later, a major task was reducing this to a more reasonable number for the analysis. So now I'll start talking about model generation. We had two different models. In general, to quote a LinkedIn blog I read recently that summed it up quite nicely, machine learning algorithms attempt to identify patterns based on the data they observe to predict future observations. So in this case, we use two different workflows, classification and regression. In the classification exercise, we hope to train the model to be able to accurately assign wells to a category of either seismogenic or not seismogenic. In classifying wells as seismogenic or not, we use the approach of Polly et al. 2018, who did a similar study looking at geological factors in induced seismicity in the Duvernay Play in Alberta. Specific criteria for seismogenic wells included if the events were within a cluster, occurred within 1 day before and 30 days after the end of a well completion, occurred within 5 kilometers of the well, and exceeded a magnitude of 1.1. Of the 2,252 wells in the dataset, 24% were classified as seismogenic. Regression is a little bit different. It provides a continuous quantitative prediction. In this case, we hope to train the model to accurately predict for seismogenic wells how large an induced event would be caused as measured by earthquake magnitude. Where there were multiple events associated with the same well, the maximum magnitude of the associated wells was taken for the regression analysis. For both problems, classification and regression, we needed to go through the same general model building process, starting with quality control of the data and then exploratory analysis of the data. And this involved things like dealing with missing values and removing outliers. At the end of it, we were left with fewer than 3,000 wells for the classification and fewer than 600 for the regression. So this isn't exactly a big data project, maybe more like medium data. And as we'll see, this does have an effect on the model results. For the exploratory data analysis, some of the tools we used included box plots and scatter plots, and we also did some correlation plots. In the box plots, we expected that features were more likely to be important if they had a significantly different distribution between seismogenic and non-seismogenic wells. The use of scatter plots revealed that none of the features showed a clear relationship with magnitude, which indicated to us that a relatively complex model was most likely needed for the regression analysis. The correlation plots helped reveal groups of features with high correlations, which means that they may represent the same process, at least statistically, and perhaps only one of the features in the group would be needed to represent the whole group. Some of the groupings these revealed included, for example, fluid intensity, proppant intensity, total fluid, and total proppant. And another group would be number of stages, average stage length, and average stage spacing. So the results of the exploratory analysis meant that only 34 completion features and 17 geological features went forward into the formal feature selection process, which is what I'm going to talk about next. I won't be commenting on the model tuning and training, but details will be included in our final report and hopefully some future publications or presentations. So for feature selection, we used both filter and wrapper methods. Filter methods apply external algorithms to measure the influence of each feature on the variance of the data. Wrapper methods iteratively assess model performance using random selection of features in order to determine the best set. We ran multiple model types for each approach, ranging from relatively simple to relatively complex, and analyzed each of the completion data sets separately. This resulted in tens of thousands of individual models run. Some of the things we had to look out for were feature interactions and confounding variables. For example, completed length, number of stages, and stage spacing interact because most wells are geometrically staged. Confounding variables occur when one variable takes importance away from another one. One of the first things we recognized was that geological features dominated all of the models and showed a lot of feature interaction. We were afraid then that the geological feature importances might be masking the importance of the completion parameter, so we decided to run the models again with completion features only. In both cases, the results between models differed significantly, and it took a surprising amount, maybe shouldn't have been too surprising, but it took a lot of human intervention to decide on the final feature sets. An example of the differences between the two completions datasets is shown here. Even after we did extensive standardization and processing until the two datasets were nearly identical, differences remained in the model results, although most of the interpretations followed similar trends. For example, these figures show a cross plot of predictors from our regression analysis, in this case total proppant in tons versus total fluid in cubic meters and maximum predicted earthquake magnitude. While the model performance is pretty similar, the complexity and trends in the model are somewhat different. In the end, we moved forward with 7 completions features and 5 geological features for the classification and 6 each for completions in geology for the regression. Note that the features are not and don't have to be the same for both problems because the problems themselves, seismogenic classification and maximum earthquake magnitude regression, are different. The selected features captured several different feature categories, including, for the completions, fluids, proppants, well design, time, and Monte development density, and for geology, depth, temperature, distance to faults, structure, stress, and pressure. Interestingly, time, including stage duration and frac duration, didn't end up being important in any of the models. We think maybe this is because this is a very operational parameter which might be controlled by things like equipment availability, etc. But that's sort of just a guess on our part. So to the interpretation piece, the models were interpreted using a number of different techniques, including feature importance and interaction, partial dependence and individual conditional expectation curves, and local model interpretability. Features with higher importance have a higher effect on the model prediction, and ideally the model should reduce or minimize feature interactions. Partial dependence plots compare the change in the average predicted value as a particular feature or features varies over its marginal distribution. This is done by holding all variables constant for each observation in the training data set and then applying the unique values of one feature for each observation. Individual conditional expectation curves are an extension of these, but rather than plot the average marginal effect of the response variable, they show the change in the predicted response variable for each observation as each predictor variable is varied. As we've already discussed, our analysis focused heavily on feature exploration and selection. When it came to building final models for interpretation, we originally fell into a classic data science trap of going straight to a complex model and sacrificing robustness for accuracy. We're really grateful to our peers who reviewed our preliminary results and encouraged us to build a more robust workflow using a spectrum of models to evaluate the trade-off between bias and variance, which I'll discuss on the next few slides. In the end, we used 3 very similar styles of models for both regression and classification. Both problems use generalized linear models, which are standard multivariate regression models, but with the allowance of a link function for classification, as well as a regularization when building our final models. Increasing in complexity, the classification models included a single decision tree, which is a directly interpretable model that can handle a decent amount of nonlinearity, and the regression model used a Mars model, which is basically a linear regression model that allows multiple slopes along a variable, or kinks. Finally, for our most complex models, we used an XGBoost for both problems. XGBoost models are pretty good at self-regularizing and are fast to train and can provide as much complexity as desired with a relatively small data set like ours. It's worth a bit of an aside here to discuss the bias variance trade-off in machine learning. There are 2 big gotchas in data science. The first is overfitting and the second is complexity. The latter is exemplified in our feature selection process, in which we had to select a handful of good, informative features from around 2 trillion possible combinations. The former is exemplified by our struggles with overfitting and leads us to balance model accuracy or bias against the model overfitting the data and generalizing poorly to unseen data or variance. In this cartoon, a perfect model would fall in the upper left corner. It is accurate for every case of unseen data. A poor model would fall in the lower right corner. It predicts poorly, and its predictions are all over the place with every new set of unseen data. Most data science problems have to find a balance between the other two scenarios. We can often get a rough estimate that generalizes to unseen data quite well, or a very accurate representation of our seen data that has a lot of problems predicting unseen data, or high variance. So if we look at the individual models for both the classification and regression, here for classification, it's really clear from the decreasing bias and variance results with increasing model complexity that a more complex model does a better job of modeling the data, although it does have a bigger discrepancy between the training and test data sets, meaning we're overfitting the data. The regression highlights the bias variance trade-off even more. So essentially, while we know XGBoost is overfitting the data, its performance still makes it the best model for the problem at hand. But we recommend it with caution as the problem is quite complex and difficult to resolve without more data. We'll finish off by looking at a local result. Well 9 of 35, 81, 18 West 6 was selected for its investigation because of its association with a relatively large magnitude-induced event. It's beyond the context of this talk to explain how these plots are generated, but the bars essentially tell you the contribution of each feature to the model results using two different methodologies. The plots indicate large contributions from the depth to the top of the Montney structure and distance from faults, both normal and Listric faults, with secondary contributions from the total proppant and mean injection rate. This is a good example of what I mentioned earlier, which is that the geological factors kept dominating the feature importance compared to the completions parameters. It's worth comparing our findings to other similar studies. In the Eagle Ford Play of South Texas, it was found that in general, simultaneous completions had the highest probability of inducing seismic activity. Specific key contributors to the higher seismic probability included effective injection rate, injected volume, and number of laterals on a pad. Key geologic contributors were proximity to faults and orientation of faults relative to the stress field. In the Duvernay Play in Alberta, where a study was focused on geologic factors only, it was found that the key factors contributing to the likelihood of inducing a magnitude 2.5 or greater event were Duvernay overpressure, minimum horizontal stress magnitude, proximity to Swan Hills reef margins, lithium concentration, which was a proxy for distance to basement, and natural seismicity rate. So to wrap up, while our study hasn't found any smoking guns, it has provided some important insight. For example, it supports, like the other studies, the importance of geologic factors and the risk of induced seismicity, which we think highlights the need to improve our understanding of the subsurface in areas being developed by hydraulic fracturing. Without subsurface data collection, uncertainty remains high. For example, in a 2012 study of induced seismicity in the Horn River in northern British Columbia, microseismic data highlighted the presence of seismogenic faults that were not previously identified on 2D or 3D seismic interpretations. There also remain some potentially important issues not addressed by our workflow, including the influence of nearby injection, and as I mentioned early on, the connection between hydraulically fractured rock and nearby faults. It's important to note that our study was purely statistical and doesn't address earthquake causation, and that the problems of non-uniqueness and overfitting were significant challenges. The bias variance trade-off is a fine line, and our results would indicate if the features would change. Our results would change if the features we included in our models changed. But even with that said, we think our consistent model results over a range of models is encouraging and indicates that we are producing realistic results. So with that, I'd like to thank you for your interest in our study. I also want to thank Geoscience BC for their support. I'd also like to remind anyone interested that our entire study, including the report, processed OGC dataset, and code will be available through the Geoscience BC website in the near future.